which has to do with introduction to networking. We've actually looked through what computer networks is all about, and then we've also explained some of the models that a computer network actually entails. So we've looked at the OSI model, we've looked at the TCP/IP model. So we actually stopped at I'm sharing my screen now, so you can see it. You can signify by letting me know. Alright, so we stopped at the OSI and TCP/IP templates, where I showed us that the OSI has 7 layers, while the TCP/IP has 4 layers, but some books actually take it as 5 layers, and we will see the reason why that was done as we proceed. Yeah, part of what will let us know is that the layers offer abstraction such that we can change a layer without affecting the upper or lower layers. You can also add to a layer without you disrupting activities of either the layers above or those below. Then also, I made it clear to us that they are both protocol stacks. That is, they have protocols stacked above one another. Then also, we're able to understand that the OSI model is just a theoretical model, while what is in practice is the TCP/IP model. The OSI model actually led to the TCP/IP model. So this we've all gone through. So today, we'll continue by looking at the concept of layering. What do we mean when we say there are different layers of the TCP/IP and the OSI model? Now, on the screen, you can see we have system A and system B, and then we have the internet in between. Now, we want to showcase how message can be sent from system A to system B, and how it's going to be delivered, how it's going to be received on the other side of the internet. Now, let's assume that the user is sending a hi message. Like I told you, I said at the application level, that is where users interact with the computer system, with the applications. So it is user application interaction. Now, the moment you send a hi through any of your applications, what happens is the application layer push the message to the transport layer, and by the time the message gets to the transport layer, there is a transport header that will be added. Now, as we proceed, we'll get to understand what the transport layer actually contains. Then from there, at the transport layer, this is application to application interaction. Then from the transport layer, it moves to the network layer. Now, the message that is being sent is I, but from transport, as soon as it gets to transport layer, the transport layer actually adds its own components. Then the moment it gets to the network layer, the network layer also adds its own component. Now, at the network layer, this is where we have connectivity. This is where connectivity actually takes place. Now, it is also sent down to the link layer. Now, at the link layer, we'll also see that another header has been added in addition to the previous layers, headers that have been added by the layers preceding the link layer. Then at the physical layer, this is where everything is converted into machine language. Last week, in the last class, I said the computer does not understand day-to-day communication. what the computer understands is zeros and one. So what we speak, the language we speak, whether English, Arabic, French, Spanish, or whatever language you speak, is regarded as high-level language. So this language is converted into machine language, which is regarded as low-level language, and that is the language that the computer understands. And that's where I define what we meant by bits, binary digits. Now, it is converted to series of zeros and one, and then the zeros and one here is converted at the physical layer to analog signal, so that it can be transported through whatever medium we have employed. So this is sent either through our local area network or through the internet to the system at the other end. Now, in practice, what actually happens is, as soon as it leaves a particular network, it gets to the other network. So it eats the network layer before the link layer. But just for us to be able to understand what takes place, that's why it's been presented in this format. Now, it gets to from the link layer. So at the link layer, the link checks whether the header matches its own or not. If it matches its property, that link header is removed, and then it is passed to the network layer. So the network layer also checks, does it meet my own properties? If yes, the network layer removes that header and then sends to the transport layer. So at the transport layer checks if it meets its property and check which particular application is expected to receive this message. And then the moment that is determined, the message is delivered. So all the communication that happens on the network goes through this process. So now we understand why we said the TCP/IP or the OSI are actually a concept of layering, and we have different protocols that operate at each layer. All right. Now, if we look at the protocol stack, at the application layer, that is where we have the HTTP protocol, we have the SMTP, we have the FTP, we have a lot of other protocols, SSH, Telnet, all of them. Every applications that we have operates with their protocol at the application layer. So, but the most common of them are the ones we have listed. Don't forget that I said HTTP is responsible for fetching web page and translating it so that it can be displayed for us to view. Now, the transport layer has the transmission control protocol, the TCP. It also has the UDP, user datagram protocol, and then it also has the STCP, that is secured transmission control protocol. All this will be explained, let me see, some of this will be explained as we proceed. Now, at the network layer, what operates is the IP and ICMP. We will explain further what an IP is and what ICMP also means. Then at the link layer, that is where the mode of communication is determined. Is the communication going to happen via a wired connection or via wireless? You can say at this point it is immaterial how the other system or the receiver of the message receives it. The message can be sent via a wire medium or wired medium, and then received at the other end as through a wireless medium. It doesn't matter. But if you look at the other ones, if a message is sent through TCP, it arrives using TCP. If it is sent through IP, it arrives using IP, and so on and so forth. All right. So now, let's now start looking at the layers one after the other, so that we can further understand what we've been saying, what we've been talking about. Now, the application layer, which we want to look at the World Wide Web as an example of an application that operates at the application layer. Now, the World Wide Web, www, is actually a web page that comprises of objects. When we say object, we mean images, we mean text fields, we mean videos, and so on and so forth. Now, a web page comprises of what we call HTML. It is a web page is always designed using an HTML language, and the HTML is Hypertext Terminal Markup Language. It is a language that is used to write the web page, coupled with some other technologies, CSS, JavaScript, and the like. Now, what you see on the screen here is a typical web page. Now, you have the URL, the Universal Resource Locator, which actually fetches the address. That's where you impute that's the address of the particular page that you want to check. Then you have the objects, text, images, videos, and the content, the body, everything that you have in the body are all referred to as objects. So that's what makes up your web page. Now, let's see how this operates. Now, at the application layer, assuming we want to fetch a web page, the protocol that is used for this particular purpose is the HTTP protocol, Hypertext Terminal Protocol. If we are sending email, it uses SMTP. If we are uploading, it uses FTP, and a lot of other protocols like that. But since we are using the web page as an example, so the protocol that handles that is the HTTP protocol, the Hypertext Transfer Protocol, not terminal. Now, it uses a browse. It's used for browsing, that is fetching HTML pages. Then we have codes. We have HTML codes which fetch out all the objects that we have on the web page, and then it uses a reliable TCP/IP protocol. Now, this I'm going to explain further. Now, if a user, you and I, opens a browser, whether Google Chrome, whether Firefox, or any browser of our choice, and we type in www.google.com, what it does is an HTTP2, a web server that is hosting the google.com domain. Then, as soon as it reaches our request, hits that server, the server fetches that page and then responds back. So, the response is what we are able to see or view on our page. But this happens through both the HTTP protocol as well as the TCP protocol. Now, let's look at the TCP now. We've explained what happens at the application layer, where we try to fetch a web page, and then we have the HTTP protocol that assists us in fetching that web page at that level. Now, at the transport layer, we have the TCP protocol. Remember, we said HTTP actually uses TCP protocol. Now, transmission control protocol is used mostly for web browsing, for file transfers, for emails, and so on and so forth. Now, the reason why it is used that way is it is very reliable, and then there is always an acknowledgement. For every message sent, there is an acknowledgement, which I'm going to display shortly. And also, there is always a delivery order. Even if the messages are not sent in an orderly manner, as soon as it gets to the destination, they are arranged. It's going to go in form of a packet, and the packets are numbered. So as soon as it gets to the destination, the order of getting to the destination does not actually matter. But as soon as it gets to the destination, the messages are arranged back to be sure that there is no missing packet. Then the HTTP is usually used for emails, for banking applications, for download. You agree with me that when you send an email, it should be wrong if a part of the email sent gets missing along the line. You want a reliable delivery. So that is where TCP comes in. If you are using a banking application, you are transacting. You send in, maybe you are doing a transaction of say 2 million naira, you send the 2 million naira. You want the receiver to actually get that value, that 2 million naira you have sent, not 200,000 or not 20,000. So you need a reliable protocol to do that, and that's where TCP actually comes handy. Now, this is how it operates. At the application layer, remember we said the protocol that operates there is the HTTP that helps us fetch the HTML page, which is the web page that gets displayed on our browser. Now, at the transport layer, what happens is it uses TCP because we need a reliable delivery agent. Now, the packets are labeled. The messages are broken into pieces and then they are labeled. Now, the first one is sent through the internet to the destination. As soon as number one gets to the destination, an acknowledgement for that particular first message is sent back to the source that, hey, I got there safely. Then it pushes the second one. Now, if the second one does not get there on time, if it doesn't get there, it keeps asking for acknowledgement. Hey, Mr. Delivery Man, you've not informed me whether that package got there safely or not. And then it will resend again until a successful delivery message is gotten. So you see that this ensures that there could be a delay, and that's why TCP is always very slow compared to UDP. UDP is very fast, but TCP is actually slower because it needs to ensure that every part of the message gets to the destination and it is acknowledged. So that is how messages are transferred or transported via the TCP protocol. Okay, so now we have the UDP, which is also a protocol that operates on the transport layer. Now, UDP is called the User Datagram Protocol, and it's widely used for multimedia. Now, UDP is unreliable. It doesn't deliver its packages in any order. That is, it doesn't send any acknowledgement. It doesn't even bother whether part of the package has dropped along the line or not. Whatever it's able to deliver is what it delivers. It's just like a bike man that went to maybe carry farm produce and is running on the road, and some of the produce are falling along the road. Doesn't care. So the moment he gets to where he is going, take your message. This is what I'm able to deliver. So that is UDP for you. So it's very fast. UDP is very fast compared to TCP because it doesn't wait for any acknowledgement, and that's why it's mostly used for video streaming, for audio calls, for live streaming. You agree with me that when you are doing, maybe you are doing a WhatsApp call, for instance, if the network breaks, you don't get to hear what that person has said. If you need to get what the other person has said, you have to now ask, what did you say the other time? Because the network broke. That is TCP for you. It doesn't care whether the message got delivered or not. It doesn't give any feedback. So that's why it's always very fast. And this is how it operates. Okay. Let's see what the transport header actually looks like for either TCP or for both TCP and UDP. Now, this is what the transport header. Remember earlier I said when a message is sent, a high message is sent, as soon as it gets to the transport layer, an header or a header is added, which is the transport header. Then if it leaves transport layer and moves to the network layer, along with the existing transport header, another header is added, which is the network header. And then when it gets to the link layer also adds its own header to all the existing headers and the message. Now, for TCP, these are the content of the header that is added. You have the source port and the destination port. We're going to understand what port means just shortly. Now, you must have on which port is this coming from? On which port am I going to get it delivered? That's number one. Number two is the sequence number. It's going to label each part of the message and then be sending them bit by bit. So that labeling is where the sequence comes in. So you label them 1, 2, 3, 4, 5, or it gives a unique number to every part of the message and ensures that as soon as it is delivered to the other end, a feedback is sent for that particular message. Then it sends the next one. It sends the next one. So if there's anyone it has not received an acknowledgement, it keeps sending that particular one until a successful acknowledgement is actually sent back. And then you have the acknowledgement number. So for every sequence number, you have an acknowledgement number, just like I showed in the previous slides. And then you have flags. In case there is an error, it gives that flag. Then check some like parity checking. It checks if the message has been altered. If it is not delivered the way it was sent, then all of these are included in the header. That is the header of a TCP. And then this is how the header of UDP looks like. So it doesn't bother. What it does is just it sends. So if there is an error, it gives a flag. There is an error, but I don't know where the error is coming from. So you see that it doesn't really bother about the source port, the destination port, the sequence number, the acknowledgement. All of these are not included in the UDP header. Alright. Now, when we now look at the two side by side, we said TCP is actually reliable. It is reliable in the sense that it sends feedback, acknowledgements for every message that is sent. But UDP is not reliable. It doesn't send any acknowledgement. Then also, out of sequence packets ordered at destination. So as it sends the packets, they are all ordered. As soon as it gets to the destination, they are arranged back in the order that they've been sent. But for UDP, it doesn't care. Then, because TCP actually takes its time to get every part of the message labeled, it gets the source and destination ports, and then try to order them, so it makes it slow. But for UDP, it's very, very fast, just like a taxi and a bike. A bike is very fast. In traffic, it will just be maneuvering. It doesn't care whether the passenger falls or not, whether the passenger gets injured or not. The main goal is let the passenger arrive at the destination. Whether he arrives with a wound, with one broken leg or whatever, at least the passenger has been able to arrive. But for a car, it takes its time. When there is traffic, it stops and all those things, so it becomes slower. You can just take that as example of a TCP and UDP. Then TCP is reliable and suitable for transfer of files. Of course, when you are sending files, you want the files to arrive completely. Then for downloads, for banking applications, for chat messages, online forums, they use TCP. But for UDP, because of the fastness, it's actually used for live streaming, live audio streams, video streams, audio chats, video chats, and so on and so forth. Okay. Now I spoke about ports. What do we mean by ports? And by extension, what do we mean by sockets? Now port numbers are actually stored in 16 bits. They are stored in 16 bits. This 2 raised to power 16. And it means what we have is we have about 65,000 ports on a particular computer system. On any computer system you have, actually it's more than that. The actual number is 65,535. but you may not get up to that extent. So out of this, 1024 is actually reserved. The first port 1024 is reserved. That's why you always hear that HTTP uses port 80, SSH uses port 21 or so, and so on and so forth. So SMTP uses port 25. So each of those ports from 0 to 1024 are reserved ports. They already have applications that are using them. So as a developer, if you develop an application, you cannot decide which port your application runs. So every application actually runs on a particular port. You can take a port number for you are going to, okay, maybe someone is coming to Kaduna to meet me. They know I stay in Kaduna, but where do I stay in Kaduna? They need to get that address. Now when they get the address, which definitely will have the suburb that I stay and the street. By the time they get to the street, they need to get to the house where I stay. They need to know where I stay. And the moment they know the house, they need to know if there are multiple people, multiple tenants in that house. So which apartment is mine? So that is like the port number. Now, using ports, we can specify an app on the system. You know, we have a lot of apps running on our system. So each one of them actually have a port number. If you go to our task manager and you try to see, let me see if I can quickly project that so that we can get to see something about that. Sorry, please. I want to stop sharing this and then we share again. Okay, I'm sharing my entire screen. I don't know if you can see that, but sorry. Okay, can you see the task manager that I opened now? Can you see it? Can anybody see it? Hello?
Yes, we can see it.
Okay. I'm trying to. Okay. Now, you see, these are different application services running on the system. And you see that each one of them has a port identification number, a port ID. So they might say this is process ID, yes, but also it represents the port numbers. So each one of them has its own port. So you find it difficult to have two different services running on the same port. It will clash. It's just like two people trying to go out through a single door at the same time. If that door is not big enough, it will be, the two of them will be choked. So one of them will have to wait for the other. So that's just about that. Let me stop sharing and then go back to the presentation itself. Okay, so now is it enough just for us to specify a port number and then we'll get our message delivered? No, we need an IP address. I kept saying that the networking layer uses IP, and that IP is what it uses to locate a computer on the network or a host on the network. So you need a combination of both the port number and the IP address and the port number. So the combination of IP address and port number is what we call socket. The port number is a unique number on which the application can be reached on a system. Now you now have the IP address. So the combination of the IP address and the port number gives you what we call socket. And definitely you have the destination. The destination is like the IP address, and then the port on that destination is the port number. Now, as you can see here, if you are running Skype and say Google Chrome, for instance, of course, Skype might be running on port 2000, just for instance, and you have the Google Chrome running on port 4001. Now, you need to have the IP address of this machine A, which is, for instance, 1.1.1.1. So a combination of both this 1.1.1.1 and either of this port number gives you what we call socket. So by the time it's being sent on the internet, now there is, remember we said the TCP will have the source and the source address and the destination address. Now the destination is this computer B, which has an IP address of say 2.2.2.2. Now the application, the fact that this application is running on port 2000 here does not mean automatically on the other machine it will be running on port 2000. It can be running on any other port. But if it is HTTP on one machine is running on port 80, and on another machine it will be running on port 80. But we may decide to say we give another port number, maybe 8081 for instance, and it is still HTTP. You get it now? So now applications can run on one port on a particular machine and on another port on another machine. So that is very, very possible. So that is why you need to have, apart from the destination IP, you also need to know which port is the application running on that machine. So a combination of the IP address and the port number gives you the socket. I hope this is clear. Okay, so now when we look at our ports, like I said earlier, I said the first 1024 ports are reserved. Like you have FTP 21, SMTP 25, HTTP 80, HTTPS 443, and so on and so forth. Now the remaining ones are unreserved, anybody can use them. So this is a pictorial representation of that. Out of 65,000 port numbers, the first 1024 ports are reserved. Nobody can use them. They are already in use. But anything above that can be allocated or can be used as one so wishes. Now there's something we also need to look at. The domain name system. It is also called the domain name service. Some people will call it domain name domain name system, domain name service, domain name which are now is 3. Okay, so let's go ahead. Human being, we can read things that are in things that we can remember easily are things that are readable, human readable. We don't actually remember numbers, like IP addresses, for instance. Now it's easier to read facebook.com and to remember that than to remember the IP address of facebook.com. Now what if today Facebook is hosting their application on a particular server using a certain IP address, and then tomorrow the address changes, the IP address changes to another IP? Does it mean we have to keep remembering those numbers? I don't know how many of us remembers the new code that NCC is using for all the mobile network providers. Remember, before we know Airtel is *123#, MTN is *556, Glo is whatever. But now, the moment they unify them, in fact, people don't even bother to cram it anymore. They will just dial *310#. Okay, take me to the next one. So this is one of the shortfalls of numbers. So for human being to remember the address of a particular system on the network, it's always good for us to use a domain name system. Now, What DNS does is it converts the names to IP. Now we can remember the name, but as soon as the IP changes, we don't know. But it is already mapped to a DNS. Now the DNS messages are always sent using UDP. That is, when DNS is trying to locate an IP that is attached to a particular service, it uses UDP because it needs a fast response. It doesn't want to make use of TCP with all the overhead that it has. And then it doesn't care whether it gets missing along the way or not. The main thing is, am I able to get the IP address assigned to this thing or not? For instance, if we were trying to search for google.com, somewhere on a particular server, google.com is mapped to a particular IP address. If you are doing hosting, for instance, the hosting site, the hosting company will definitely have their own servers and IP addresses that you can map your public domain to. And you can also decide to map your public domain to your own public IP. We're going to explain what public IP is later. Now, if you have your own server and it is connected to a public IP, you want to give, of course, you don't want to give your IP address because that will make your system to be vulnerable to attacks. So you have a registered domain, and then that domain is linked to your IP. So tomorrow, if you change your ISP, you don't need to change your domain. Your domain remains, but you can always change. You can always map a new IP to it. So now, what happens when you send a request, say google.com? What it does is it goes to a kind of repository to check which IP is mapped to google.com, and then it replies your system, oh, I found it, this is the IP. Then your system in the background now uses that IP to eventually locate the server on which google.com is hosted. Okay. Now, for DNS, there are hierarchies of servers. We have the root DNS. The root domain name services, they are just 13 in the whole world. They are just 13. So this is where you have, this is where domains are actually registered. And then you have the top level domain. When you say top level domain, we mean .com, .ng, .net, .africa, .io, and so on and so forth. Those are top level domain. Then you have the authoritative. Now the authoritative is where an actual domain is mapped to a particular top level domain. Say abc.com, google.com. So that is the authoritative now. Okay, this is what happens. If you are looking for Stanford University, for instance, what you do is you type that on the browser, and then you send a request. That request goes to a top level domain server. It first goes to the root DNS server. Now the root DNS server replies that, okay, this particular domain you are trying to access is hosted on a top level domain of .edu, not .com. Okay, it sends that back to you. Then your system automatically sends a request to a .edu platform, which is a top level domain. So the top level domain now searches for the name that matches the one you are looking for, and then send this back to you that, okay, this is the server you need to contact. Then the moment you get that, our system now sends an IP. I mean, as soon as it gets the Stanford.edu server, it sends a request to that server requesting for the IP address of this particular domain, so that I can keep communicating. And then the moment the server now replies that this is my IP, that is now cached in the memory of that system, so that when next you are requesting for Stanford.edu, it quickly scan through its own cache memory, or cache. Some people call it cache, some people call it cache, but it's a temporary memory where information are stored, so that it doesn't delay requests when next you need it. So this is how DNS works. So it actually assists us in remembering some organizations or websites that we need to visit without us even bothering whether the IP address has changed or not. So DNS also operates at the application level. Okay, having said that, before we come to a stop and allow for question and answer. Now, at the network layer, this is the relationship that happens between the layers. Now, I have my computer system. I know every application that runs on it has a socket, which is a combination of the port number on which the application is running, as well as the IP address of that machine. Then, at the network level, it's routers that operate there. So these are the devices that operate at different levels now. At the application level, we have our computer systems. It could be our phone, it could be our PDUs and whatever. But at the network level, it is router that operates. So routers are devices that help us to look for the best route to get to a particular destination. And what do they use to do that? They use IP addresses. So at the link layer, that's where we have our switch. The switch, remember when I was talking about types of attack, I talked about man-in-the-middle attack. That what it does is it poisons the address resolution table, address resolution table of the switch, and then injects the attacker injects his own MAC address against the IP address of a legitimate user, so that he can always receive, and that MAC address works in a promiscuous mode, such that he can receive all messages sent on that link. So if they ask you which device actually operates at network layer, that is the router, and then we have switches at the link layer. But I also mentioned that we have switches that are also layer 3. They operate at both link layer and the network layer. So the reason why some groups actually believe that TCP/IP is 5 layers is this. Now, if you say it is 4 layers, and then we merge the physical and the link layers together, that would be we will call that layer 1. But why don't you now say switch operates at layer 1? Because in the recent they don't operate at layer 1, they operate at layer 2. And then router operates at layer 3. So a router is a layer 3 device, a switch is a layer 2 device. You understand? So that is about network devices that operate at different layers. Now, I'll be stopping here. We'll be looking at IP protocols, the Internet Protocol. So I'll just give you a brief introduction to that, so that we take some of our questions before we round up for today. Now, at the network layer, the protocol that operates there is the IP, as we have seen earlier. And when we say IP, it means Internet Protocol. So, Internet Protocol, routers actually uses Internet Protocol to get the destination, the source and destination of a particular message. And this is an example of how an IP address looks like. Then the properties of IP is it is connectionless. It doesn't really transmit. It doesn't really transmit any loss packet. It doesn't really transmit. It's the upper layer, transport layer, which uses TCP that does that. Then packets can take multiple routes, and packets can arrive in any order. Okay, so going back to our TCP model, we see that application layer we have our HTTP, FTP as sample of some of the protocols that operate there. At the transport layer we have TCP and UDP. Now at the network layer we have the IP. And then at the link layer we have the MAC address. Now at the physical layer, that's where the conversion is done, and then which medium are we using to transport or send our message. Now this is what happens. Now this is how an IP works. The router has what we call routing table. You know, the switch I said has address resolution table. Now the router has a routing table in which it keeps the address of all the routers on the internet. Now, a computer connected to one router A and that needs to send message to another computer connected to router B will go through its own router by sending the address of that computer on router B to its own router. Now, that router is connected to different other routers. So what a router does is it's an intelligent device. It looks for the best route. It's just like you call Uber. Your Uber picks it and then comes in and then looks at the best route to your destination. It will tell you to give different, it will give the driver different routes. Okay, this route there is congestion right now, there is traffic on the road, you might take 45 minutes before you get there. But this particular one is though longer, but at this rate now, you can get there in the next 30 minutes. You understand? So you don't take your decision. So how does a router take decision? It uses something called routing protocols. The routing protocol we have IRP, Internet Routing Protocol, we have the OSPF, Open Shortest Path Protocol, we have the IGRP, EIGRP, and so on and so forth. So it uses that to determine which of this is the best route for it. And then it gets that, okay, let me say, instead of going through router C before getting to router B, why don't I just send my packets to router B? But if there is traffic along this route, it can decide to say, okay, even though from C, you send it through C, it will be longer, but the packet will get delivered earlier than if I send it through A. And then the message is sent through the best destination, the best route, and then it gets to the destination using the IP address. So at this stage on the internet, what operates is the IP address. Okay, with this we'll come to the end of today's class, and tomorrow, Wednesday when we meet, we'll look at, we'll continue with IP address and different types of IP addresses. Thank you so much.
All right, thank you very much for the beautiful presentation tonight on the continuation of the last domain, which is on network domain. So without wasting much of our time, we have just less than 5 minutes to close this session. If you have any question, if you have any clarification, please unmute and ask your question now. Thank you very much.
Good evening.
Yeah, good evening.